Doesn't it automatically report to
Like I'm wondering, like, oh, yeah, so they just see you. Just because, like, I try and read doing the same thing. This one's not. Yeah, I was hoping that this class would be the same.
Good afternoon, everyone. Welcome to class. It's nice to have you here. This is biochemistry, principles of biochemistry, Chem 481, and I am Stephen Graves. I'm the instructor for the class. I'm looking forward to getting to know each of you better as we go along. I don't know how many were able to participate online for Monday's class, but I do have a syllabus that I'm going to distribute, a hard copy, and also I have an administrative matter that I'll discuss in just a minute. So if I can have my TAs distribute these. In fact, let me introduce, so this is Jason Wild, who's one of the TAs, Rebecca Burlett, who is second TA, and I don't know if is Josh here? So we have, we have Josh as well, who's a TA, Josh Ballard. So I would get to know these individuals, and they will, here's Josh. So Josh, raise your hand. He's the third TA. They will establish their own office hours. You'll see on the handout and also on Learning Suite that I have office hours, including office hours today, starting at approximately 3 o'clock. As soon as I get back from this class to my office, I will initiate those. Most of these, I assume, will be done via Zoom. If you have a need to do it in person, that's fine as well. You're also welcome to contact me at other times during the week. So I have formal office hours, but I'm willing to visit with you at almost any time I'm in my office, which is much of the day, 5 days a week. So please avail yourself of that if you have questions or issues, either about course content or other matters. In just a minute, we're going to distribute a sheet here that refers to something called FERPA. It is the law protecting your privacy. We will have some graded materials. It is our hope that we can return these to you by placing them in alphabetized bins between a display case over in the Benson building. This is in the main hallway towards the west side of the Benson. I'll give you more details when it becomes relevant, but the quizzes, as I mentioned on Monday, there'll be, I anticipate 5 of these. They will be group quizzes, or can be group quizzes, with up to 5 participants per group. And so those will be returned in those bins. Likewise, at this point, we will be taking exams in the testing center. The schedule is on that handout and also posted on Learning Suite as well. Typically, there are multiple days in which you can take the exam, giving you a little more flexibility. But those materials we would hope to return to you as well in these boxes, these bins beneath the display case. Now, you're welcome to have these not be placed in the bins in the hallway of the Benson, which is a public area. It is conceivable that someone would go over to the bins and pull out an exam. They wouldn't be able to see your scores on the front sheet of the exam. That doesn't happen, but if they opened up and went through the interior, they could determine what your point scores were for sections within the exam. If you would rather not have them placed in the bins, then you will need to schedule times to come pick them up at my office. So that is the other option. They can either be placed in the boxes, in the bins, or you can come pick them up at a time that works for both of us. Okay. Any questions about that? Yes.
So with those quizzes being returned in the bins, are they going to be submitted online still and then printed off, or will they be something that we hand in physically that will be returned into the bin?
It's likely that, so in the past, it has been a combination of both.
Okay.
Some of them have been hard copies that have been turned in class or to my office or to the Chem offices. Others have been submitted online, printed off, evaluated, scored, and put back in the boxes. So it's a little more work if we had to print them off and then rescan each of them and then send that out to each of the members of the group. I guess that could be done in individual cases, but preference would be that there's a single copy submitted per group, it gets graded, and then you pick it up and tell each member of the group what happened. So.
Thank you.
Yeah. Other questions? Online questions? If you do, please send these as a chat, and the TAs are monitoring the chat and can let me know if there are other questions. Okay, so here are the FERPA sheets. You'll see that there are 2 options, if you can get those out. One is to pick them up, or a willingness to have them be placed in the bins. The other is a desire to pick it up at my office. So please put your name, sign it in the appropriate line, and you can turn those in. You can pass them to the edge of the rows, or you can turn them in at the end of the class, whichever is easiest. All right. Let me sort of reiterate what I said sort of at the end of last hour. And that has to do with personal issues. So I don't drop exams, I don't drop quizzes. However, if there are circumstances that require you to be gone from campus, it could be a family wedding, your own wedding, it could be an interview, a presentation at a meeting, whatever. If you will let me know, we can arrange something so that we can work around your schedule to allow you to take exams and to complete and turn in quizzes. But I need to know those kinds of things in advance. Don't come 2 weeks later and say you had this great opportunity to ski in France and you missed the exam. Can I make it up now? I won't be very receptive to that, okay? However, if you tell me that you have something going on and you need to leave, then we can work around it. For emergencies, please let me know as soon as possible, or have somebody, a friend, a family member, let me know if that there's been an emergency. And again, I'm happy to work around the problem if I am apprised of it in a timely fashion, so within a couple days of the problem. Additionally, I would mention that if you have things going on in your life that will perhaps impact your performance in the class, then please let me know. I don't need to know the nature of the problem or per se, but if there are issues around effective learning for you, if there are issues around your circumstances, your health, whatever, please let me know so that I can be sensitive to your needs and be as accommodating as possible to allow you to be successful in the class. I have had on a few occasions people come finals week and tell me about things going on, and I apologize for this mask. If I talk, it gets pulled down. Tell me about problems they've had during the semester, and they're real problems, and I'm very sympathetic, but at that point in the semester, there's really almost nothing I can do. But if I know about things as we go along, then very often a workable plan can be developed to allow you to be successful in the class. Okay, enough on that. Another thing that I mentioned last class is that the exams focus heavily on a few things. The questions that appear on the exams are on topics that are covered in class. There will be reading materials that you are asked to read that will not be on my exams, but could well be on your MCAT or DAT exams. So, in fairness to you, I will tell you to read these pages. However, what we cover in class represents the material asked about on exams. If we spend more time with a particular topic, the more questions will appear on that topic on the exam, and the level of detail will be greater. At the beginning of every class, I will list out things that you should know. That's just the way I use to identify sort of the important aspects of the class for the day. These are the things that will be asked about or will be part of questions that appear on the exam. So here's a heads up. Some of these may not be asked about directly. In other words, I won't ask you to calculate the pH of a buffer, but it is important for you to understand what buffers are used in our body, how in effect they work, And so they do come into play as we consider these various topics. Okay. I am going to move back and forth between slides and sort of the board here. It's going to be a little awkward until I get a little bit more proficient at doing this. So I ask you to bear with as we do this. Let me pose a question though to the people who are online. Can you hear me sufficiently well? So if there's a little thumbs up or thumbs down somewhere on Zoom, if you could simply, I'm good, okay. At least one person thought it was okay. Okay.
Yeah,
Okay. All right. I'll try to enunciate as clearly as I can. It is obviously more difficult to do this through a mask and so forth. Okay. At the end of last class, I posed a question. Let's see if I can find it here online. Well, let me just begin. Actually, I'm going to talk a little bit about. Let me give you some context, and we will go to the question I asked earlier.
There are some questions from the chat.
Yeah. Okay.
So another one is, can we assume if a topic is not covered in class, it will not show up on exams?
That is correct. So if a topic is not explicitly discussed in the lecture, it will not appear on the exam unless I specifically indicate that you are to study something on your own, because it will appear on the exam. That happens very rarely. Occasionally it has happened. So, yes. Additionally, prior to each exam, about ideally a week before the exam starts, I prepare a study guide, a review sheet that lists out the specific topics on that exam and the number of questions on that particular topic, on each of those topics, to give you a sense of how to allocate your time for studying. Okay. Let's see. Where do I? Let me bring up the board. Okay, how do I move? Let's see. I need to go here to. Okay. So at this point, the people online are just seeing this slide. So let me go through this a little bit. In order, is there a way to lose that header up there? So all of biology, all of life, all of what we consider when we talk about physiology or pathophysiology involve interactions between molecules. Our body has to hold together. Our body has a wide variety of different functions, everything from locomotion, movement, all the way down to what happens within a cell, and so forth. All of this involves these molecular interactions. Those of you who have been through organic chemistry and have talked extensively about covalent bonds and breaking and remaking covalent bonds. And there are many, and most molecules in the body are held together through covalent bonds. However, much of biology, much of physiology does not involve covalent bonds. It involves molecules made with covalent bonds between atoms, now interacting one with another in non-covalent ways. And we'll talk substantially about that over the course of the semester. So these can involve such things as protein-protein interactions, forming complexes, These can involve other types of biomolecules interacting one with another. So think of a cell membrane comprised of phospholipids, no covalent bonds. And yet we depend entirely on the integrity of tissues and cells on these types of interactions. We have enzymatic reactions. Most of the metabolism, most of the synthetic processes, almost all of the synthetic processes in our body involve multiple enzymatic steps. These, again, do not typically involve covalent interactions. We have the substrate, the material to be acted upon binding to the protein, being converted into a product, which in turn then becomes substrate for another enzymatic reaction. These do not involve typically covalent bonds. And so we need to understand then the complexity, the nature of these other types of interactions. Regulation throughout the body does not involve covalent bonds. It involves these types of intermolecular interactions that are extremely important, but are not due to the making and breaking or breaking and remaking of covalent bonds. Okay. So that's the context for some of what we're going to talk about today. Okay, let me ask you then to help me list various kinds of chemical bonds. Okay, so I've already talked extensively about one kind that, please, what are some chemical bonds, types of chemical bonds? Yes?
Hydrogen bonding.
Okay, hydrogen bonding, okay. Yes? Ionic, okay. In the context of biology, we sometimes talk about these ionic bonds as ion bridges or ion pairing. It's the same concept, plus attracts minus and so forth, holding things together, but sometimes they are not referred to, well, sometimes they don't explicitly use the term ionic bonds. Other ideas? Yes?
Van der Waals.
Okay, van der Waals, okay. Okay, a couple more that we should consider. Yes?
Dipole interactions.
Okay. So dipole. Okay. And the final one that should appear up here is we just mentioned about breaking and remaking covalent bonds. Okay. So this covers really the range of bonding interactions between atoms and molecules. So covalent being the strongest typically, ionic bonds, hydrogen bonds, dipole interactions, and van der Waals. Van der Waals is also sometimes referred to as London dispersion forces or transient dipole interactions. So it goes by a couple names. Okay, so here we are with some actual energies associated with these. This gives you a sense of how strong, relatively strong, these different types of interactions are. You don't need to memorize the number of kilojoules per mole, but it gives you an idea that something like van der Waals, London dispersion forces, are extraordinarily weak. And if you're talking about relatively small molecules, nonpolar molecules, such as nitrogen gas, you have to chill that gas to extraordinarily low temperatures to be able to form even a liquid. Otherwise, there's so little attraction that these molecules disperse and stay apart naturally all the time, or at least at room temperature, okay? All right, so here's the question that was posed at the end of last hour. We have in our body double-stranded DNA. Double-stranded DNA is comprised of 2 copies of DNA. The order of bases is reversed between the 2, but nevertheless, they form this very nice helical structure, and this is how these exist primarily in living systems. What's shown here is a heating curve, a melting curve, and you can see, maybe I should do this. This is too complicated. Anyway, you can see that as a function of temperature, so what you're looking at is as temperature goes up, we go from double-stranded DNA up to single-stranded DNA. In other words, we are disrupting the bonding interactions between these 2 strands. So the question is, what's holding these together? Okay? What is the primary interaction that is holding these 2 together?
Hydrogen bonds.
Hydrogen bonds are very important, but they are not the primary bonding interaction. They're less than 50% of the binding energy between double-stranded DNA. Okay, well, you don't know because, probably because this is what we're going to talk about for the next few minutes. The bonding interactions between double-stranded DNA, while hydrogen bonding plays a very important role, the predominant bonding interaction between these 2 strands is termed hydrophobic interactions or hydrophobic bonds or bonding. Now, when we talk about hydrophobic molecules, non-polar molecules, we typically think of them as having almost no attraction for other hydrophobic molecules. Let me go back 1 slide. If we consider London dispersion forces, this is what we have with nonpolar molecules. You can see that there is vanishingly small bonding interaction between hydrophobic molecules. So why then, or how then, is it possible for these hydrophobic interactions to be so important and so much more substantial than you would predict based on the enthalpies of interaction between hydrophobic molecules? So that's really where we're coming from. This concept is non-intuitive. I'll just tell you right at the front of this that it is non-intuitive. It's going to take you some time to wrap your head around this, but they are extraordinarily important. Yes?
On one of the first slides, it said that organic reactions often involve covalent bonds under extreme conditions, and then biochemical also have covalent, but also use IMS. Is biochemical a subset of organic, or are those two different groups that you're referring to?
So I think organic chemists would say that everything is subservient to them. So, but in answer to your question, you can think of biochemical reactions as being a subset of organic chemical reactions. However, the problem is that when we talk about organic chemistry and when organic chemists talk about organic chemistry, they primarily are talking about forming a compound. They want a particular product, and here's the way you make compound X. So if you're trying to synthesize a new drug or modify an existing one, they're talking about all these fancy reactions to bring that about. probably 80 to 90% of the reactions that we'll talk about, maybe more, do not involve the breaking and formation of covalent bonds in biochemistry. So yes, they do involve chemical reactions that are between organic in the sense we're talking about hydrocarbon kinds of species, but we'll see that the biological reactions are a little different than what we would typically encounter in an organic chem course. Yes?
There's a question, does this mean that dropping DNA in oil will instantly denature it?
This is a really good question. Question, if you didn't hear it, was, would dropping DNA in oil denature it? First of all, we haven't talked about what denaturing means, but if you're talking about disrupting DNA by dropping it in oil, the answer is probably not. However, the question is relevant, and there are, well, we will see that it has relevance as we continue on. So I don't think it would, but I guess you'd have to do the experiment to see. Okay. So to be able to understand hydrophobic interactions, we need to consider water, especially in the context of biology. So water, as we know, is a small molecule. It has the ability to hydrogen bond in several different directions. Okay, so you have the ability, let me go to the board here. Okay, here's where things get crazy. Okay, so share. And skip first. Okay. Stop share. Oh. Okay. What's that? Okay, let's go back here. This is going to help with it. Okay. All right. All right. Thank you. So here's this idea that somehow, so water then is able to form hydrogen bonds in multiple different directions. It's able to, so we have here the oxygen. It has these lone pairs of electrons, and we have these two hydrogens. The hydrogens now can interact with lone pairs of electrons on another water molecule. These lone pairs can interact with the hydrogen on another water molecule. So each water molecule, in effect, can have 4 hydrogen bonded water molecules attracted to it. In solution, a water molecule will change partners every 2 times 10 to the minus 11th second. So pretty quickly. Okay. So in effect, they are loosely tumbling about, freely tumbling about in the bulk solution of water. Now imagine that we take a hydrophobic molecule and we insinuate it, we insert it into an aqueous environment. Okay, so let's say this is our hydrophobic molecule. And what happens then is that while this is the water generally is tumbling about very rapidly, those water molecules that have to interface with the hydrophobic molecule now cannot simply tumble about endlessly. Half of the area, the volume around any water molecule is lost when you place it against this other surface of this other molecule. Additionally, to be able to continue to form hydrogen bonds effectively, it causes the other water molecules around it to be oriented in a particular, more, a less free orientation. In other words, the water molecules that lay against the side of this object are going to be far more ordered. Okay? So ordering means a reduction in what? Entropy. Okay, so this is energetically not ideal, not favorable. That's why hydrophobic molecules have very limited solubility in water, but they have some. But it does mean that you have effectively a monolayer of water molecules surrounding this object that are ordered. Okay? This ordering is sufficient that sometimes this is referred to as a lattice, almost as if you had a crystalline structure. It is also sometimes referred to as a cage, a hydrophobic cage. So, a water cage, a hydration cage surrounding this hydrophobic object. Okay. Now, consider what happens if I have two molecules that are hydrophobic. So let's say that on this surface that has some blue here, this represents, all of the surfaces have this layer of ordered water molecules, this hydration cage around them. But consider what happens now when I bring these two molecules together, okay? All of the water molecules on this surface, all of the water molecules on this surface are displaced by allowing these two molecules to interface one with another. What does this do to the number of ordered water molecules? It decreases it. Okay, and depending on how large the hydrophobic interface is, small, larger, maybe you could have very large hydrophobic surfaces, the number of ordered water molecules displaced, becoming disordered, goes up proportionally to the surface, the interface between these two molecules. Okay, so let's consider for a moment bonding energy. And we're going to do this in the most general of terms. These are thermodynamic terms. The Gibbs free energy is equal to the enthalpy, this delta H, which is what we saw on the slide indicating that van der Waals forces were extremely weak. But we also have this second term. This is absolute temperature, and this is entropy. So as entropy goes up, the bonding interaction between these two molecules becomes greater. Larger hydrophobic molecules being allowed to interface one with another increases the bonding energy substantially. Okay. Are you with me so far? Questions? This is conceptually weird. Okay, yes?
So does that mean it's energetically favorable if those two come together because there's less caged water around it?
Absolutely. So the question was, does this mean that these two, there's more energy or more attraction between these, attraction is not the right word, more bonding energy between these two molecules by allowing them to come together? And yes, absolutely. And the more surface, the more the interface between these two, the stronger that interaction is. So if you think of long strands of DNA, well, then that can produce very substantial quantities of bonding energy in that process. We think about membranes made up of fatty acids or phospholipids. those are going to be fairly large and those bonding interactions fairly strong. Okay. Now, how would I get these apart? This goes back to the question, if I drop double-stranded DNA in oil, will that lead to a disruption, a loss of bonding energy between these two molecules, or multiple molecules? What is it that's holding these together? Really? Yes?
The entropy of the water.
Okay, so it really is the water, the hydration cage that is holding these together. There is no repulsion between hydrophobic molecules and water. There isn't. There is no attraction, effectively, between hydrophobic molecules. The van der Waals forces, the enthalpies for those are negligible. So it is the hydration cage, this drive to minimize the number of ordered water molecules that are holding these together. So what might be a strategy for breaking these apart? Yes?
Heating up the solution?
Okay, heating the solution would probably work, okay? Another, perhaps, okay, so some disruption of the hydration cage then would indeed allow these to come off. Now, the simplest way, or the way that is often used, at least in the laboratory, is to take a small molecule, an organic molecule that is water soluble, miscible with water, something like methanol, ethanol, that can hydrogen bond, okay? So it can substitute for other water molecules, but the binding energies for something like methanol to water are weaker, and something like methanol, you have a portion of it, you now have a, sorry if you can't quite see this, you now have this appendage that can't hydrogen bond. So now you begin to disrupt, you begin to poke holes in the hydration cage. You create incongruities in this hydration cage. The more you do this, you weaken those hydrophobic interactions. And well, at some point, as you increase the organic solvent concentration, these will simply fall apart. The other possibility is simply to remove the water. Okay, I'm going to close with one example. We'll talk about acids and bases next time. Everybody's so excited to talk about them anyway, but let's consider meringue. Okay, what is meringue? Does anyone know? Anybody cook, bake? Yes? Egg whites, okay? What are egg whites, okay? So if you open an egg, you see this sort of clear, relatively colorless, it's not that clear, but it's sort of this translucent, colorless material, and then you have the yolk. And it turns out that the egg whites are a solution, an aqueous solution of a protein called ovalbumin. Okay, and to form meringue, you start to beat this. This is a very viscous, a very thick solution of ovalbumin. And as you beat it, you create bubbles. And the bubbles now represent air that is surrounded by this solution of, aqueous solution of ovalbumin. And as you beat this more, what happens? Stiffer and stiffer. Now, what does stiffer and stiffer mean? It means that these proteins are unfolding. Okay? Think of them being relatively globular, spherical in nature. As we beat this, they begin to unfold and they begin to precipitate out of solution. They become a solid, which makes it stiffer. If you really want to make these stiff, what do? You bake it and you drive off more water, okay? So what's happening? These bubbles represent this very thin layer of water, and you allow the water to evaporate. And as the water evaporates, you denature those proteins. They become insoluble, and they begin to form solids, and you can make them stiffer, or you can make them more rigid and brittle and more of a solid by baking these in the oven. And so your cookies can be quite crunchy if you make them that way, or the meringue on top of your lemon pie is quite crunchy. Okay. Questions about this? So hydrophobic interactions, hydrophobic bonds represent a reduction in ordered water molecules surrounding two or more hydrophobic compounds. We're going to find that many of the interactions that we talk about, substrates binding to enzymes, proteins coming together to form complexes, receptors or pores in the surface of the cell, all of these things depend heavily on these hydrophobic interactions. If we can't maintain an aqueous environment, then we denature proteins, they lose their function. If we want to separate hydrophobic compounds, we can do so by substituting compounds that hydrogen bond less well, and they disrupt this lattice, this nicely ordered series of water molecules, and suddenly these compounds will separate and come apart. Thermal energy, as was mentioned, can also do the trick. We saw this with double-stranded DNA. You simply heat that solution, thermal energy is converted into kinetic energy, and suddenly those hydrophobic interactions are insufficient to hold the two strands together. Okay, any questions about this? We'll come back and talk about we'll talk about acids and bases next time. I'll give you a few more examples of hydrophobic interactions. It's important for you to understand this concept. It's not that you'll be asked probably specifically about it, but it underlies a lot of what we'll be talking about hereafter. Yes?
So with the removal of water, that also breaks up the lattice just because there are less molecules to go.
Yeah, if you want to think of it, you can think that the water molecules are actually compressing these other hydrophobic molecules. They're actually, and what you're doing is the drive is to make the surface of this as small as is possible. That reduces the number of ordered water molecules, increasing entropy. This force then is actually observed as things being pushed together to form these hydrophobic bonds. Other questions? Online questions? Yes?
How much of an effect does a change in enthalpy have in these reactions? Or would you say that that's
Negligible. Yeah. All right, let me begin a story, okay? Many years ago now, the Olympics came to Salt Lake City, 2002. There's still reminders of this. If you go here and there, there's still some of the symbols of the Olympics and so forth here and there. The summer before the Winter Olympics, I was at a town fair, and there was a booth there, and there were some individuals who were recruiting people to serve as volunteers for the Winter Olympics. It was understood that there would need to be a lot of people involved to make these successful. And so I signed up. It turned out that the university encouraged students, faculty, staff to get involved in the Olympics and to volunteer their time, not necessarily as classes, but to nonetheless volunteer their time to make the Olympics a success. Well, it turned out that this particular group that we're recruiting people for what was called the Olympics Medal Plaza. It turns out that in prior Olympics, someone would ski the slopes. You would have all of the skiers go down doing the slalom. And after a couple runs, they would determine who had the 2 fastest times. And immediately they would give them their medals. So right there on the slope, they'd put out a little wooden stand, and they would climb up and they'd drape them with their medals. But for the Salt Lake Olympics, one of the innovations was that they had centralized award ceremonies. That meant that people would gather down in the center of Salt Lake. Typically 25 to 30,000 spectators would come to this Olympic Medals Plaza. You had to have a ticket to get in. The tickets were free, but you would come there and they would actually have this award ceremony where all of the medalists would come on stage, receive their medals, and the applause of the audience. They also had entertainment. They had really, at that time, big name groups: Backstreet Boys, Bare Naked Ladies, Dave Matthews Bands, Garth Brooks, Nelly Furtado. You probably don't even know who these people are, but back then, they were the big, they were the real deal. And then they would have fireworks at the end. They'd send off, they had this big fireworks display at the end. And so this is where I was located for the several days that I participated as a volunteer. Well, one night I was put on the VIP entrance. That is to say, that was my station, and my responsibility was what was termed mag and bag. I would make sure that all of the people coming in would go through a magnetron, a metal detector, and then I would go through their bag. And quite literally, it was a table no wider than this. And so these individuals who were coming in through the VIP entrance would set down their camera case, their backpack, their fanny pack, their purse, whatever, and would go through and make sure there were no weapons and so forth. This was shortly after 9/11, and so tensions were pretty high, and people were trying to be very, very careful. So this gave me the opportunity to get very close to these medalists, the people who had medaled that day. Now, the other members of the Olympic teams went through the general entrance. They were out in the audience, and you could see them. They had special uniforms, most of them. And you could say, oh, that's somebody from the Norwegian team or the German team. But these people that were coming through the VIP entrance were those who had medaled, who had actually placed in their events. Okay, I'll tell you more next time. Thank you.
We stopped the recording.